All right, so we are going to do section 4.1 as it says right here. We're doing rational functions and asymptotes. Um, these are going to be the things that we cover. We're going to talk about what an asymptote is. And you guys may know what an asymptote is already, but we're going to go through a formal way of looking at it. So we'll do that. We're going to talk about a rational function, but that's super easy. And then we're going to look at how to find the asymptotes. And most of today is actually going to be spent on horizontal asymptotes. Um, it turns out there's going to be a shortcut that we can take, but I don't want to just give you the shortcut without you guys understanding the shortcut. So we're going to go through why the shortcut works, and that'll take a little bit of time. But then all this other stuff, the relationship, and then the actual graphing, it's actually not that bad once you get through all the other stuff. So with that said, let's do it. Um, so the first thing is, what is an asymptote? Now I know you guys have seen asymptotes before, but, and actually, well, I guess I'll stop right there. So an asymptote is a line, and I'm going to put that in quotes because actually we don't always have to have lines as asymptotes. I'll give you an example today. And the graph approaches is at the ends, but that's kind of a, how do you define end? But it doesn't settle on, like, this is a weird definition. This is not a very formal definition. Let's look at it more formally. So here's a couple of examples. And these are examples of rational functions. I didn't actually give you the equation, but that's okay. We don't need to know the equation. But we can see there is a vertical asymptote. There is a horizontal asymptote. This one, second one, has two vertical asymptotes. Whoa. And a horizontal asymptote. And so we can see, that the graph at the ends is approaching the asymptote, but it doesn't actually settle on it. It never actually reaches it. If we could zoom in, we'd see it's still not there, it's still not there, it's still not there. But let's look at these more formally. So let's look at the first one. And by the way, for the rest of the unit, instead of writing out the words horizontal asymptote and vertical asymptote, because they're kind of long and honestly time consuming to write, I'm always just going to abbreviate HA and VA for horizontal and vertical asymptote. So let's look at the horizontal asymptote as y equals 1. So we can see very clearly from the graph that this is it, but here's a way to look at it more formally. And we can use our end behavior notation that we've learned before. As x approaches negative infinity, so remember that means as the x values go to the left, because that's approaching negative infinity, we can see that this graph is approaching the asymptote. We were used to the graph going up or down with polynomials, but now it's going to approach an asymptote, and in this case it's approaching the asymptote y equals 1, so we say f of x approaches 1. The function approaches a value of 1. And then the same thing on the right hand side. As x approaches positive infinity, f of x approaches 1. And so now we're more formally defining what we mean by it. For our vertical asymptote, now this gets a little weirder. We can see in this picture that the vertical asymptote is at x equals negative 1. However, we have to, now instead of saying as x approaches negative or positive infinity, as x is going to the left or to the right, x is actually going towards this asymptote. So the value of x is approaching negative 1. And it's actually, the graph is actually doing two different things on either side. It doesn't always do different things, but these examples I did. On the left-hand side, to the right of the vertical asymptote, we can see the graph is going down, or f of x is approaching negative infinity. But to the left of the asymptote, we can see that the graph is going up, so it's approaching positive infinity. Now we could write these in words, but I always like to say, mathematicians, we're efficient. We're not lazy, we're efficient. So how do we say this? How do I say, as x is approaching negative 1 from the right-hand side, that the graph is going down without using all those words? I say it like this. As x approaches -1. And when I want to say -1 from the left, I put a little negative sign up there where an exponent would normally be. So that means -1 from the left. We can see that the function is going down, meaning it's approaching -infinity. And then as x, oh my goodness, except that's x is I don't know my left and right. That should be from the right. Hang on one second. Let me say this again. As x is approaching -1 from the right-hand side, it's going down. So make sure you've put a plus sign right there. That's how we're going to say as x is approaching -1 from the right. Make sure that's a plus. And then on the left, we're approaching -1 from the left. The function is going up, so we're approaching positive infinity. Let's take a look at the second one and see if you guys can write the horizontal and vertical asymptotes like we did on the top one. So we know we have a horizontal asymptote at y equals -1 in this case. So can you write it using that x approaching, f of x approaching notation? And we have a vertical asymptote at x equals -1 and a vertical asymptote at x equals 2. So try that right now, see if you can write it in that notation, and then we'll take a look at it together. Oh well, let's take a look. So this is what you should have gotten. So again, for the horizontal asymptotes, we don't care what's happening in the middle. It's all about what's happening on the left and the right-hand side. So for the horizontal asymptotes, you want to look at what's happening as x is going to the left and as x is going to the right, or approaching negative or positive infinity. And in this case, we're approaching this horizontal asymptote of -1. And then for the vertical asymptotes, so we're approaching, and it doesn't really matter if you put from the left or from the right first. That part's kind of arbitrary. But if I go from the left first, we can see that the graph is going down. So as x is approaching -1 from the left, the function is approaching -infinity. As we're approaching -1 from the right-hand side, we can see that the graph is going up. So as x approaches -1 from the right, the function is approaching positive infinity. And then likewise for the other asymptote. Now, we won't bother writing this, but I wanted to give you this third example. I mean, we could go through the same exact thing, but we're not going to. But what I want you to see from this third example is it's possible to cross an asymptote. A lot of people learn an asymptote as a line that the graph never crosses, but gets closer to, which is a good definition to learn in the beginning, but it's technically not correct to say that. The graph can cross an asymptote. It's all about what's happening at the ends of the asymptote. So that's the reason I wanted to give you this one. And then here's just some other examples of asymptotes. Asymptotes don't have to be only horizontal and vertical lines. They can be diagonal. In fact, in the next lesson, next class, you'll learn how to find these slant asymptotes. But you can also have asymptotes that are quadratic. And rational functions could have these. We're not going to get that complicated this year, but it's possible to have a quadratic asymptote. You could have a cubic asymptote. You could have any polynomial be an asymptote. And then you could even have asymptotes like this last example, where the graph is crossing all over the place. But what I was trying to draw there is as it's bouncing, it's getting closer. The bounces are getting smaller and smaller. So it's getting closer and closer to the asymptote, but it never actually settles on it. If I could zoom in on the graph, you would see it's still going up and down and up and down and up and down. And there are graphs that look like this. This is not a rational function, though. Rational functions won't do that. But these first two could be rational functions. But like I said, this year we're going to keep it kind of simple. We're going to have horizontal and vertical asymptotes today. In next class, we'll learn about, slant asymptotes. So let's talk about what a rational function is. There's really nothing special to it. A rational function is simply a polynomial over a polynomial. That's it. That's why it's coming after our polynomials unit. So When you divide two polynomials, you create a rational function. Now, how to find the asymptotes? Let's look at that. Now, the vertical asymptotes, they're also very simple. Here it is. Vertical asymptotes occur when the denominator is 0. Boom, done. But horizontal asymptotes, like I said earlier, that's where most of the meat of today's lesson is going to be, is horizontal asymptotes. And now we're there. Let's do it. So I'm going to give you 3 examples we're going to go through together. And they're going to be a little long, but the purpose of the examples is for us to develop a shortcut. You will not have to do this on every single problem. There will be a shortcut that we're going to get. So let's take a look. Let's just start with this example. Let's say f of x is 3x squared minus 7x plus 12 over x minus 9. It's a polynomial over a polynomial. We have a rational function. So here's a strategy that you could do that would formally find our horizontal asymptotes. So remember, our ultimate goal to find a horizontal asymptote, we want to know what's happening as x is approaching positive or negative infinity. What does f of x approach? If we can find that, that'll be our horizontal asymptote. And a way we can do that is we rewrite f of x. And here's how we're going to rewrite it. First, I'm just going to write it. I'm not going to change it. We have 3x squared minus 7x plus 12 over x minus 9. And I'm going to multiply by a form of 1. And that form of 1 in this case is 1 over x squared over 1 over x squared. The reason why I'm choosing x squared is because 2 is my biggest exponent in the problem. Between the numerator and denominator, 2 is the biggest exponent. So I'm choosing x squared because 2 is the biggest exponent. Oops, can't spell exponent. In the function. So I'm basically going to divide the top and bottom by x squared. So what that's going to look like is f of x equals 3x squared over x squared minus 7x over x squared plus 12 over x squared all over x squared minus 9 over x squared. So I've just made it really ugly. What I'm going to do is I'm going to simplify each one of those individual fractions. So if we're going to get f of x equals, in the first one, the x squareds cancel out, so I'm just left with 3. So I have a 3. In the second fraction, there's an x in the numerator that will cancel with one of the x's in the bottom. So I'm going to be left with 7 over x. And then I'll be left with 12 over x squared. In the denominator, I'll have 1 over x minus 9 over x squared. Okay, so now let's see what we've got here. Remember, what I'm trying to do is what it says up here. I'm trying to find out what's happening as x approaches infinity and negative infinity. So let's look as x is approaching infinity. Now that I've rewritten f of x, I can look at each one of these little individual pieces. This first piece 3 is 3 is 3. It's a constant. So it doesn't matter what x is approaching. 3 is not going to change. 3 stays a 3. But the second fraction, 7 over x. As x approaches infinity, since x is in the denominator, what's happening to this fraction? If the denominator gets bigger, then the fraction gets smaller, right? So the bigger and bigger the fraction gets, the bigger and bigger the denominator gets, the smaller and smaller and smaller the fraction's going to get, and it's just going to keep getting closer and closer to 0. So I can say that second fraction approaches 0, and this third fraction, this third fraction down here, again, it's got an x squared in the bottom. So as x approaches infinity, this denominator is going to get bigger even faster. But either way, the whole fraction itself is going to get closer to 0. And even on the bottom, we're going to have 0 minus 0, because there's an x in the bottom of these guys as well. So as x is approaching positive infinity, f of x is approaching 3 over 0. What's 3 over 0? Yep, it's undefined. So that means we don't have a horizontal asymptote, and that happens sometimes. So there's no horizontal asymptote for this guy. And the same thing would happen whether x is approaching positive or negative infinity. The value of each one of these fractions is still going to be 3, 0, 0, 0, and 0. We're still going to have an undefined value. That means it's not approaching a number we don't have a horizontal asymptote. So let's try another one. And let's see. We'll line up the things. So let's try this guy. Let's find the horizontal asymptote for f of x equals 5x squared minus 3x plus 2 over 4x to the fourth minus 7x squared plus 8. Oh my goodness, this is crazy. Okay, so we're going to do the same kind of thing. We're going to first rewrite f of x. So we're going to say that f of x is, I'm going to take the original function, and I'm going to multiply top and bottom by a form, or I'm going to multiply by a form of 1. Can anybody tell me what's going to go in the top or bottom on this one, based on what we did before? Yeah, I'm going to multiply by 1 over x to the fourth over 1x to the fourth, or divide by x to the fourth. And again, we're picking x to the fourth because that's the biggest exponent, whatever the biggest exponent is. So now I'm going to divide each term by x to the fourth. Thank goodness we're not going to have to do this every single time, huh? And then we can simplify each one of those fractions. So it'll simplify to 5 over x squared minus 3 over x cubed plus 2 over x to the fourth over 4 minus 7 over x squared plus 8 over x to the fourth. So now that we have this, now we can look at what actually happens as x is approaching. And like I said, it's going to happen, it's going to be the same exact thing, whether it's positive or negative infinity. But we can figure out now what f of x is approaching. And just like above, Anytime you have an x still in the denominator, if x is approaching infinity, that means the denominator is getting bigger, which means the fraction is getting smaller. It's getting to 0. So we're going to have in the numerator 0 minus 0 plus 0, and the denominator is 4 minus 0 plus 0. And if we were to simplify all of that, what would we get? Yeah, we're going to get 0. And there were a few people that put either x equals 0 or y equals 0. In this case, remember, we're talking about the function approaching 0. This is a horizontal asymptote where y equals 0. So we can write that. We have a horizontal asymptote. At y equals 0. Yay, we got one. All right, so the example is going to look like this. And maybe, since now you know that we're going to get an integer value that's not 0, maybe you could try to predict what it is about this problem that's going to make that. So let's say we have 4x squared minus 3x plus 7, just making these guys up on the fly, over negative 2x squared plus 5x minus 8. So again, we're going to do the exact same thing we did before. So why don't you guys try it now on your own? Try doing the exact same process we did on problems above, where you're going to divide each term by some power of x and try to rewrite it and see what you get. And this time I'm actually going to pause my screen. All right, so this is what you guys should have gotten. And I had a lot of people predicting what it was going to be, why, and all of that. And as you can see, we definitely get, it approaches a number that's not 0. And one person saw that you could basically just ignore all the numbers, all the terms that don't have the biggest exponent. Like in this case, 2 was the biggest exponent. All these other numbers go away then, and it's all about these terms, the 4 and the negative 2, and 4 over negative 2 was negative 2. So it winds up that with this one, you know you're going to have a horizontal asymptote at y equals some number besides 0 when the degree is the same on the top and the bottom. So well said for everybody that was getting it. Even if you didn't write it and you were thinking it, well done. So if the degree is the same on the top and the bottom, you can just look at leading coefficient over leading coefficient. 4 over negative 2 is negative 2. So your horizontal asymptote is at negative 2. If I look at the problems above, when y equaled 0, our biggest degree was on the bottom. That gave us a 0 on the top and a 4 on the bottom, because we could ignore all these numbers. So if the biggest exponent is on the bottom, that means you have 0 on the top, which makes it 0. And in the first example, if the biggest degree was on the top, that's why we wound up with 0 on the bottom, and that was undefined, so that's no horizontal asymptote. So we can summarize that all in this box right here. And this is going to be the shortcut we can take. We don't have to do all that work anymore. All we have to do is look at the degree of the top and the bottom. So if we have a rational function, and n is the degree of the top, and m is the degree of the bottom, if it's a bigger degree on top, there's no horizontal asymptote. If it's a bigger degree on the bottom, the horizontal asymptote's at y equals 0. And if the degree is the same, the same, then it's just y equals leading coefficient over leading coefficient. And you literally can take that shortcut. You don't have to show any work to get the asymptote, the horizontal asymptote. But now we know why it works. So, any questions about that? We just made it through the hump of the lesson. We're on the downhill slope now. Yes. Oh, you guys are awesome. Yeah, if you want to write this part down. Somebody's asking, can we write this part down? So I'll go ahead and pause right here. Give you. All right, so let's think about this. Can we cross the asymptotes? Let's think about the horizontal asymptote first. What do you think? Can you cross a horizontal asymptote? And I actually already gave you the answer to this, but you may have forgotten because we just did it quickly in passing. And I'm seeing a few people putting it in the chat. Yeah, the answer is yes, we can. And I'm just going to say this, but I'll go up there. See the examples on page 1. Let's go to page 1 really quick. Right here. Remember, we can cross the horizontal asymptote. Because remember, the key is not what's happening in the middle. A horizontal asymptote is what's happening as we go to negative or positive infinity. What's happening on the left or the right hand side, not in the middle of the graph. It can do whatever it wants in the middle of the graph. That won't affect the horizontal asymptote. It's all about the left and the right hand side. So, yes, we can cross a horizontal asymptote. So what about a vertical asymptote? Can we cross one of those then? And yes, excellent. Ashton's got it. It won't be a function. So no, it won't be a function. And he's describing it. It won't. It really won't. It won't be a function. Let's just draw a graph to kind of show what's happening there. Let's say we had there's our asymptote, and let's say that we had something like this. I mean, that could be what it's doing. Maybe it crosses here, but remember, by definition, we have to look at what's happening at the end. At the end, if this is a vertical asymptote, it's got to be approaching the asymptote at the end. But if it has to bend back on itself, it's going to fail the vertical line test. It won't be a function. By the way, one thing I want to make clear too, when you're drawing your graphs, you should always draw in your horizontal asymptotes. But the asymptotes are like helper lines. They're not actually part of the graph, but they're there to help you draw the graph. So that's why your horizontal or your asymptotes in general should always be dotted lines. Anything that's dotted isn't actually part of the graph. Yeah, it's kind of another variation of the vertical line test, somebody's saying. It's because of the vertical line test that it won't be a function. So then, the whole point of that, what does that have to do with what's in pink, the relationship of the vertical asymptotes in the domain? Because a graph can never cross a vertical asymptote, that means that's a value that's not part of the domain. Because there's no function value right there. It's an asymptote. So the vertical asymptotes always create restrictions in the domain. Now I'm wording it like this on purpose. I'm not saying that the domain is exactly coming from the vertical asymptotes, because next class we'll actually learn about you can have holes in your graph. So there can be other places where there's gaps in the graph that aren't asymptotes. So we don't have to worry about those today, but that's why I'm wording it this way. But so wherever there's a vertical asymptote, it's a restriction in the domain. But you can't say a restriction in the domain is because of a vertical asymptote. That won't be true. That's all I needed to say about this. Any questions about that? See, we got through the horizontal asymptote part much easier. So then, looking at the intercepts, there's really not a lot to say here, but again, we can take a little shortcut. So that's the only thing I really wanted to point out here. We know in general, to find an x-intercept, you let y equal 0. So if I have this function, r of x is n of x over d of x, if I want to find the x-intercept, let y equal 0, I let r of x equal 0, but a fraction will only equal 0 when the numerator is 0. So your shortcut for rational functions, if you want to find the x-intercept, just set the numerator equal to 0. That's all. So you can write this top part down if you want, but the part in the green box is what's important. To find the x-intercept, you set the numerator equal to 0, but the y-intercept you still let x equal 0, like normal. So now we're ready for examples. And don't worry, we just said a lot of words. I want you to see with the examples, don't be overwhelmed and think, oh my God, there's so much. This homework's going to be so hard. It's not as bad as it seems, trust me, because we have all these shortcuts. Does anybody need this, or can I scroll up to our examples? Okay. All right, so let's look at these two examples first. I want you guys to try them first based on what we've done. So find the domain and horizontal or vertical asymptotes of these. And we didn't talk a whole lot about the domain, I know, but at least try to find the vertical and horizontal asymptotes. And if you can find the domain, we'll take a look at a second. So there really isn't any work. So you can see all that work we did in the beginning was to help us understand the shortcut, but the shortcuts are so easy. So on the first example, it was the same degree on the top and bottom, so you can just do leading coefficient over leading coefficient. 3 over 1 or just 3. Y equals 3 for the horizontal asymptote. Vertical asymptote. Set the denominator equal to 0, and if you don't get a real solution, because remember we're talking about graphing on a real plane, yeah, we could say the answer is plus or minus I, but that doesn't give us an asymptote, because we can't plot x equals I on a real plane. So if there's no real solution, there are no vertical asymptotes, and you can have rational functions like that. And then if there's no vertical asymptotes, we don't have any restrictions in the domain, so this ends up being our final answers. And by the way, please, 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 when you're showing your work on a test, notice how I was labeling what my work is for. Let's find the horizontal asymptote, and here it is. Let's find the vertical asymptote. Please do that. We're going to have a lot of things at the end. We're going to have asymptotes, we're going to have intercepts, we're going to have holes, we're going to have slant asymptotes eventually. We're going to learn how to know if a graph crosses one of the horizontal asymptotes or slant asymptotes. So there's a lot of work. And if you just do it all in one big jumble, but you don't do something right, I'm going to have a lot of trouble trying to find partial credit. So label your work so I know what you're doing. On the second example, the horizontal asymptote's a little weird because we have this extra 2 hanging out there. But again, if you think about what we were doing previously, we were trying to find out what happens as x approaches infinity or negative infinity. The 2's not going to change. That 2 is still a 2, but this fraction will approach 0. So we can say the horizontal asymptote is at y equals 2 plus 0, just y equals 2. So that's the way you think about it. And this time we did get some real solutions for when we set the denominator equals 0. So then we do have restrictions in the domain that correspond directly to our vertical asymptote. So you could write your answer like that. So I just have one more example. I want to do a graph with you so you can see what a graph would look like. But any questions about this? So somebody's asking about the is it the domain or the vertical asymptote? Can you write the vertical asymptote as x equals plus or minus 1? And the answer is yeah, you can. I just like to write them separately because honestly, I see it happen all the time where if you write the plus or minus, then oftentimes when it comes to actually graphing, both of them don't get graphed. You might have x equals plus or minus 1 written, but then when you graph it, for whatever reason, a lot of people forget about both of them. So I like to make it very clear there are two unique vertical asymptotes. And yeah, so like up here, the plus or minus up here in my work, that's showing me I've got 2. But notice in the final answer, I did separate them. You don't have to. Technically, you don't have to, but I like to do it. Okay, let's look at one more example. Does anybody still need this stuff before I scroll up? Okay. We'll do this last one together, but let's look at this graph. Now, for us right now for graphing, we really only have 4 things. We have vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts. So let's find them. Let's see how just knowing that we can get a pretty decent graph. So if you want to think about on your own, like the horizontal, vertical, all of that stuff, I'm going to go ahead and work it out though while we're doing it. But if you want to try it on your own, you kind of ignore what I'm saying. But for the horizontal asymptote, this time I have it factored. But we still have to think of the degree of the top and the bottom. So you're going to want to think of this thing all multiplied out. But it's like our end behavior from the last unit. You don't actually have to fully multiply out the top and the bottom. It's all about that leading term. So if we do x times 2x, we'll have 2x squared in the top plus some other stuff that we don't care about. And in the bottom, we'll have x times x plus some other stuff we don't care about. And then we can clearly see it's the same degree on the top and the bottom. And we can also see that what the leading coefficients are. So we can see the horizontal asymptote at y equals 2 over 1 or 2. So as we find stuff, I'll put it over here. We know y equals 2 is our horizontal asymptote. Vertical asymptote. Just set the denominator equal to 0. But now we can see x equals -3 or x equals 2. So again, very little work, and we can find our asymptotes. Any questions finding those? Okay. So then the x-intercepts. Remember our shortcut. Normally you just let y equal 0, but for these guys it's all about the numerator. So set the numerator equal to 0. So then we can see that x is -2 or 3/2. Now for your x-intercepts, I really recommend this. Technically you could write them like this. You could say x equals -2 or 3/2, but now they start to look like asymptotes. And again, I see it happen all the time, especially students that aren't clearly labeling all the parts of their work. They start to think that these are vertical asymptotes, or maybe these are intercepts, and so they graph it wrong. So instead, what I would recommend is writing them. X-intercepts are points, so write them as a point. We have -2, 0, and 3/2, 0. But I'm going to say the same thing that I did with the asymptotes. It's okay if you don't write them as points, if you say x equals -2 or 3/2, but don't just say -2. What's my x-intercept? -2. I will take off for that. You have to say x equals -2. You have to put that x equals in there, or you can write it as a point. So we want to be mathematically correct in our notation. And then the y-intercept, we have to let x equal 0. So if I just go back up here and fill in a 0 for all of these x's, I'm going to wind up with 2 times -3 on the top and 3 times -2 on the bottom, which is just, it's just 1. So the y-intercept is 0, 1. So any questions how I found all that stuff? Because believe it or not, we have enough to get a pretty decent graph of this function. I'm going to go ahead and set up my graph. Okay, so I'm going to go ahead and plot. Oh, wait a minute, there's a question. Let's see here. Okay, I'm going to go ahead and draw in everything we know. We know we have a horizontal asymptote at y equals 2. I really should have. Hang on one second. So we know we have a horizontal asymptote at y equals 2, a vertical asymptote at x equals -3, and x equals +2. And we have x-intercepts at -2 and 3/2, 0, and then a y-intercept at 0, 1. And that's all we need. We now know our graph. So here we go. Here's how you graph a rational function. First of all, your vertical asymptotes always divide the graph into these intervals. In this case, because we had 2 vertical asymptotes, we have 3 intervals. You will always have a branch of your function in every interval. And because it's got to pass the vertical line test, that branch will either be above or below the horizontal asymptote. So on the left, it's either going to be above or below. In the middle, it's either above or below. And on the right, it's either above or below. Now the middle is easy because all the action, we can see these points down below. So all the action's happening below, it's got to be below. So we know that we have this right here. Now, please show your branches getting closer to the asymptotes. What I see all the time, I see something like this. Don't do that. This is not getting close to there. I want to see the branch getting close to the asymptote, because that's the definition of an asymptote. If you do something like this, I will take off. Show that it's getting close to the asymptote. Now, let's look at the left. Like I said, the branch is either going to have to go above or below. Does anybody know which one is it? On the left-hand side, will it be above or below the asymptote? You're on the right track. So close. It can't be below, but not because of crossing the vertical asymptote, but because of crossing something else. If the graph was below, what am I crossing that I'm not supposed to cross? Yeah, exactly. If it's below, I'm making an x-intercept where there's not one. So yeah, very good. Now, I do get some students that do this. They'll put it below, but have something like this. But again, remember the definition of our asymptotes. The x-axis is not an asymptote. We didn't find that. We found this line y equals 2 as the asymptote. That means at the end, this graph has to get up to approaching the asymptote. It's gonna have to cross the x-axis if we try to draw below. So yeah, a lot of people were putting in the chat, the graph is above on both sides for the same exact reason in this case. We cannot cross that x-axis. We can't make extra x-intercepts. And if you were to draw this on Desmos, you would see that that's the graph. So you just figured out how to graph this function right here that looks pretty complicated with very minimal work, and you got a pretty decent graph without just plugging in random values of x. So well done. Yeah, it does kind of look like a Mickey Mouse face. And that is it. So have fun with the homework. Bye.